Another concept in logic is a predicate. Now, a predicate is a logical statement whose truth value is a function of one or more variables. And the truth value depends on a variable, and this is not a proposition. Remember that a proposition is a statement that is either true or false. So let's look at a predicate. So here's several predicates, and the way we say this is P of X. So this is a predicate P of X. X minus 2 is greater than 5. So is that true or false? Well, it depends on the value of X, right? When X is 20, then it's true. When X is 3, then it's false. So we can't say that X minus 2 is greater than 5 is either true or false because it depends on the value of X that we're using. And that's what makes it not a proposition. It's a predicate. It's a function that is either true or false based on the variable itself. So here's the first one, P of X, is dependent on a single variable X. Q, the next predicate Q of X and Y is dependent on two variables. It depends on both the value of X and the value of Y. And R is a predicate that's dependent on three variables, X, Y, and Z. Now notice that here, these three have just used mathematical expressions, where S of X is more of just a statement. So the predicate S of X is that X is a prime number. And notice that each one of these predicates are dependent on the variable itself. So let's go back and look at those conditions. The truth value depends on a variable, and it is not a proposition because of that, because it's dependent on a variable. So that's what a predicate is. Now, what is a predicate when we think about programming? So a predicate in programming would be a function that returns true or false, and the value of that is dependent on the input. So on the parameters of the function, right? On whatever arguments are sent to that function when it's called. So a function that returns true or false and is dependent on the input or the arguments that are set for those parameters. And that's what that would look like when you're talking about a predicate in programming, a function that returns a Boolean value. Domain is the possible values for the variable. So when we're talking about P of X, what kind of values can X be? Could it be an A or a B, or does it need to be a number? Now, in this case, it seems very clear that this would be an integer if we were just going to pick it, rather than a character, because a character minus 2 doesn't make sense. But we could specify what the domain is, that maybe the domain is all integers, which means it would include negative ones as well, or maybe the domain is all positive integers. We can specify what those possible values are, and we call that the domain. And the domain might be something like an infinite set, like the set of positive integers, that's infinite, or it might be a finite set, like the set of students in this class. There's a certain number, a finite number of students in this class, and that could be the domain. It could be a set of finite numbers that are just spelled out in a set. So here the domain might be 3, 7, 12, and 15. So those are just examples of what a domain might be. Now we can quantify, we can use a quantifier with a predicate. So here we have the predicate P of X. We recognize that as a predicate. And this quantifier, that upside down capital A, says for all X, or for every X, P of X is true. When we put a quantifier on it, it now becomes a proposition because we can identify the truth value of it. We say for every X, P of X is true. Well, is that the case or not? Let's try it to find out if that is, okay? So here, what we're going to use is we're saying for every X, P of X, X minus 2 is greater than 5. And we have specified that the domain is the set of positive integers. So let's find out if for every X this is true or not. So let's take X 28, and we take 28 minus 2. That is in fact greater than 5. That means it is true. But can we find even one? When we use the universal quantifier, right, if we use for every, all we have to do is find one that's not true to make the whole statement not true. So let's see if we can find one. Let's take 6. 6 minus 2 is greater than 5 is false, right? Because that's saying 4 is greater than 5, and that's false. So we have found one value in the domain, one value for x, where this is false. And so then when we say for every x, p of x is true, that's false. And so we've been able to identify that this proposition is false. And so as soon as we put a quantifier on it, it becomes a proposition, and we can identify the truthfulness of that predicate. Well, of that proposition, right? Another quantifier that we can use is the existential quantifier. And this one says there exists an x where p of x is true. And so this isn't saying all of them, it's just saying there exists. And it can be a single one, but it says there exists an x where p of x is true. Again, this is a proposition. Once we add that quantifier, that predicate combined with the quantifier is a proposition. And we can identify that it's true if we can find a single value that returns true. So let's apply this to the same predicate that we've been using and say there exists an x where p of x is true. So if we use 3, then we do 3 minus true, we see that it's false. So we haven't shown this yet because we've only shown a false one. But if we can find a true one, so let's take 14. 14 minus 2 is greater than 5, and that's true. So we have found one that shows there exists an x where p of x is true. And so we've been able to establish the truthfulness of this proposition. So a predicate is not a proposition, but when we add a quantifier, then it becomes a proposition. Another time that a predicate is a proposition is when it has a specific value. Instead of just being the variable, it is actually called with a specific value. In this case, it has a truth value and it is a proposition. Let's look at a couple of these. Consider the proposition q of x comma y, and that is y is greater than x. When we call it with q 12 comma 15, those are actual values from the domain that we can use, and we can determine that this is true because 15 is greater than x. When we call it with q 91 comma 83, we can identify that this is false because 83 is not greater than 91. And so both of these are propositions. They have a truth value that we can determine, and it's not dependent on the variable because the values are sent. One more time, here's s of x, where x is a prime number. If we call that specifically with s of 8, then the truth value is false. If we call it with s of 13, then the truth value is true because 13 is a prime number.